do me a favor real quick and grab something heavy nearby. Maybe something that you can hold like this bowling ball. We're gonna do a little demonstration with this. So thinking about carrying this bowling ball, the easiest way for me is to keep this thing as close to my body as possible. I want you to take the same object that you have in your hand and I want you to slowly move your arm out more and more and more and more. Now the weight of that ball doesn't change, but the further away it gets, the harder it feels to hold. And that's what we're talking about today is moments. So a moment is kind of the effect of a force, like a turning effect. So that if I were to let my shoulder slack, my arm is going to rotate down because of that force. So keep in mind, moments are not forces, but it's kind of an effect of a force. And the things that impact the moment an object has is the amount of force acting on that object and the perpendicular distance it is away from that fulcrum. And that produces what we call a torque, but we're not super worried about that for right now. Let's do a quick and easy calculation regarding moments. So we have a lever here, and our effort force is on the far left side. We have a resistance force on the far right side. And we have a distance from the fulcrum to our effort force of 5.5 inches. So what we are trying to figure out is what is the moment that the effort force provides to this lever. So to start us off, we're going to try to figure out the moment, and our equation is the force times its perpendicular distance. But notice how the force is straight down compared to the horizontal lever, so we don't have to do any fancy trig stuff. It's already perpendicular. And so we can transform that equation just a little tiny bit. In our case, we're talking about the effort force and the effort distance specifically. So I'm going to modify my equation just a little tiny bit. And I'm going to toss in the numbers to calculate that out. Notice how I have my units with my numbers every single time. And when we type it into our calculators, we have 82.5 inch-pounds. Now those units are super important. You may be using feet, we might be using newtons, meters, centimeters, whatever, it doesn't matter. But we need to make sure we're reporting the unit for moment based on the calculations that we did prior. So this force produces a moment of 82.5 inch-pounds. Let's move to a more useful application of moments, and that is static equilibrium. So let's say that we have a lever and we have three different forces that are acting on it that are going to create a moment or a force that's going to force that thing to rotate. So static equilibrium is a condition where there are no net external forces acting on that body so that it remains at rest or makes it move at a constant velocity. So for our purposes, what this means is all of these forces, all of these moments together needs to make sure that this lever stays still. So if one side is more unbalanced than the other, we're going to have a rotation. That's not a good idea. So let's kind of put that to the test. Let's try out our calculation to see how this works. So I have three different forces that are acting on this lever. I have an applied force by me, so maybe I'm sitting on there or pushing it down, something like that. I have a resistance force on the far side that is 4 inches away from our fulcrum. And I have an unknown force that's a little bit closer to the fulcrum, about 1 inch away from that thing. So what I'm going to do is, knowing all of this information, I need to figure out how much force does that thing have to act so my lever maintains static equilibrium. Now, one thing to pay attention when we're talking about static equilibrium is this only works if you have a perfectly ideal lever. So if there's any friction, any outside forces that are messing with this system, this does not work. So what I would highly recommend is you use IMA and AMA in efficiency more often than you try for moments. But sometimes we're going to have to use moments to solve some problems. So let's do that. Let's figure out everything that we know. So we know we have an effort force of 15 pounds. We know that distance is 5 inches. We know there is a resistance force on the far side of 6 pounds. We know that we have a distance from the fulcrum equal to 4 inches. We know the distance that that second resistance force is acting is 1 inch away from the fulcrum. And the thing that we're looking for is that resistance force number 2. I'm going to call that FR2. So we've annotated our work. We've identified everything that we know and are unknown. So we're going to start pulling from those equations to try to solve the problem. So for moments, I'm going to start with the bare minimum and I'm going to continue breaking it down. Keep in mind that static equilibrium is not really an equation. We're using moments to conceptually solve for these values. So in my head, I know that however much moment this force gives us, it has to be equal to the combination of these two over here. So I'm going to say the moment from our effort force, I'm going to say ME, is equal to the moment of our second resistance force, I'm going to say MR2, plus the moment provided by that first resistance force. So this isn't really an equation that we have necessarily. We just have individual moments that we know to maintain static equilibrium. The moments over here have to be equal to the moments over there. So let's start breaking that down. So I know the equation for a moment is force times distance. So Fe times dE equals Fr2 times dr2 plus Fr1 times dr1. So I have my equation set up. If you prefer to isolate for that force right now, you could do that, but I'll kind of work through the actual math if you want to keep watching this part. So I'm going to start plopping in numbers, and we know all this stuff right here. I'm just going to insert it for each individual piece within my equation. So I have 15 pounds, and notice every time I'm going to include those units. 5 inches is equal to FR2, whatever that ends up being, times dr2, which is 1 inch, plus Fr1 is 6 pounds, times dr1, which is 4 inches. Whew. Okay, now I have all that stuff set up. I'm going to plop those values into my calculator, do a little bit of algebra, and we're going to solve this thing out. So I'm actually going to grab my calculator right now. So if I multiply these two together, I have 75, and I'm going to say inch pounds. So I'm just combining those units, kind of multiplying them together like we would an actual value, is equal to Fr2 times 1 inch. I'm just going to leave that there. And then do the same thing over here is 24 inch pounds as well. Cool, so let's keep it going. I'm going to take 75 minus 24, see if I can't isolate that. Whoops, typed in the wrong number there. So I have 51 inch pounds after I subtract that 24 over is equal to Fr2 times 1 inch. And we have one last thing we have to do. We do have to divide by 1 inch. And the reason that's important is if I divide everything by 1 inch, that's going to help us a lot with our units. Divided by 1 inch. So we have 1 inch going away on that side, and we have inches going away on this side. So we find that Fr2 has to be equal to 51 pounds based on that unit that's left. So notice how the closer you are to the fulcrum, you get much less bang for your buck. That's a huge amount of force compared to these two, but because it's so close to that fulcrum, the moment is actually relatively small compared to these two things. So keep in mind, moments, we're calculating the perpendicular distance from the fulcrum times the amount of force acting perpendicularly, and static equilibrium, we're just trying to figure out if the moments equal up on both sides to maintain static equilibrium or your lever not moving at all.